Hello guys. In previous videos I explained increasing decreasing functions, local extrema and critical values, and now we are going to solve some questions and see how to find increasing and decreasing intervals, local extrema and critical value of each kind of function. We will be studying every kind of function. So first function we are going to find one of each is polynomial function. So let's take a look at the first question. Exercise question, an administrative question. It's a polynomial function. We are asked to determine increasing, decreasing intervals, local extrema, and critical values one by one. So remember, in order to find the critical value, we have to find the numbers that make derivative 0 or undefined. So since it's a polynomial function, there is no value that make the derivative undefined. We will only check the numbers that make derivative 0. So let's just take the derivative then. F prime of x equals take derivative of 2x cubed, which is 6x squared, plus 2 times 3, 6x, minus 12. Equalize derivative to 0. 6 is extra here, it's a common factor. We can take 6 out as a common factor or divide everything by 6. So we will have x squared plus x minus 2 equals 0. When you factorize it, you'll see it is x plus 2 times x minus 1 equals 0. So x is equal to minus 2 and x is equal to 1. I got two values. So if these two values make the function, original function, defined, then they will be our critical values. So do we know that f of minus 2 and f of 1 are defined? Yes, of course. When I insert negative 2 back, I'll have a number in the result as a result. When I substitute 1 back for x, I'll get a number as a result. So those two are defined. We can also say since the function is polynomial, no matter what number you insert, it's going to be defined. So those two numbers, the function at those two numbers are defined, then we can say x equals negative 2 and x equals 1 are critical values. So I answered the first part of the question. I got my critical values. Second part, find increasing and decreasing intervals. In order to find increasing and decreasing intervals, the best way of figuring out which region the function increasing, which region decreasing is making a table of variations. So let's make table of variations. We have two numbers, negative 2 and 1, from negative infinity to positive infinity. Here I have f prime, here f. Okay, so when I pick a number more than 1, put in the derivative and see what the sign is. To determine the sign of each interval, we have to pick a number from each region. Or there's a simpler way. We can check the coefficient of the sign of the leading coefficient here, which is positive. So on the right, start with positive, change the sign for each number, negative, change again, positive. But this is not always safer, because sometimes we have double roots and we have to keep the same sign on each side of the number. So I don't recommend using this way. You picking a number from each region is the safest way. When you pick a number right side of 1, like 2, put 2 back and see the sign, it is positive. Pick a number between negative 2 and 1, like 0, put it back and check the sign, it is negative. Like that, find the sign of each region. And we know that if the derivative is positive in a region, then function is increasing at that region, right? Derivative is about slope. Remember, if slope is positive, then the function is increasing. If slope is negative, then function is decreasing. Positive, increasing, like that. Whenever the derivative is positive, function is increasing, negative, function is decreasing. So this table helps us to determine increasing and decreasing intervals. So increasing intervals are from negative infinity to negative 2. Union, we have another part, 1 to infinity. Decreasing intervals, only one interval from negative 2 to 1. So we never include these numbers. We always used open bracket because at these numbers the derivative is 0, neither increasing nor decreasing, right? So one last part about the question. We checked increasing decreasing intervals. Now it's time to find local extrema. So what do you think about the extrema? The extrema occur at critical values. So whenever function is increasing at first and then decreasing, there is local max. Here, for example, increasing at first and then decreasing, there is local maximum at x equals minus 2. Function is decreasing at first and then increasing, there is local minimum at x equals 1. Okay, this is how you find local maximum and minimum. After you make the table, you will find increasing intervals, decreasing intervals, and local extrema. Everything depends on this table actually. But keep in mind that if those numbers are not critical values, we don't have local extrema, even though we have increasing first, decreasing, or decreasing first and then increasing. So we have to make sure that these two numbers are critical. Otherwise, we can talk about local extrema. Okay, this was the first question. Second question, another type of question, another type of function. This is a rational function. So for a rational function, can derivative be 0? Can derivative be undefined? Think about it for a second. The derivative can be 0. So let's equalize derivative to 0 first. F prime of x is equal to, what is the derivative? Let's use some shortcuts. I'm sure everyone knows this by heart without even doing the steps. Negative 2 over x cubed is the derivative. So we have two conditions. First, derivative being equal to 0. Second, derivative being equal to undefined. Do we have a 0 condition? Let's see. In order for a rational expression to be 0, numerator should be 0. So for whenever you have a rational expression, to equalize the derivative to 0, you just equalize the top to 0. Negative 2 equals 0, which is impossible. So there is no critical value from this case. What about the second case? Derivative being undefined. What makes a rational expression undefined? Denominator being 0 makes it undefined. Let's check the denominator. We have x cubed. Equalize it to 0. Then x is equal to 0. Does it mean that x is equal to 0 is a critical value? We don't know. Remember the definition. In order for us to know whether the result is critical value or not, we have to make sure that it makes the function defined. So when I put this back in the original function, f of 0, is this defined? 1 over 0 undefined. So x equals 0 is not a critical value. So we don't have a critical value for this function then. No critical value. So the second part of the question, if we don't have a critical value, how can I make a table? How can I find increasing, decreasing intervals then? So making table of variation doesn't depend on the critical values. Whether we have a critical value or not, we have to make the table. How are we going to make the table? We are going to make the table by using the numbers that we found from the derivative, from either first case or from the second case. We have to use the numbers along with the critical values. So we don't have to have a critical value to determine the test intervals. X values that are not in the domain of f also determines the test intervals. So let's make a table of variations. Even though 0 is not critical value, we have to do this. From negative infinity to positive infinity, f prime f. Okay, when you pick a number more than 0, like 1, put it back in the derivative. It is negative 2 over 1, negative. This part is negative. When you pick a number less than 0, like negative 1, negative over negative, positive. So positive region means function is increasing, negative region means function is decreasing. See, there is this motion, increasing at first and then decreasing. Even though the increase the function changes from increasing to decreasing, there's no local extrema. There's no local extrema. It looks like there's a maximum here, but there is no maximum here because that number is not a critical value. If that number is not critical, it doesn't yield a local extrema. So no local extrema, no critical value, no local extrema. But we can still determine increasing and decreasing intervals. So increasing intervals from negative infinity to 0, exclusive, decreasing intervals from 0 to infinity. That's it. This is a way of solving the question. We have, of course, another way. If you are familiar with the graph of this function, 1 over x, 1 over x squared, negative 1 over x squared, 1 over square root of x, 1 over absolute value x, these kind of basic functions, you are familiar with their graphs more probably. So you can use their graphs instead of solving, instead of doing all of this stuff, just do the graph as a second way. So this is how 1 over x squared graph look like. From right and from left, the parts are increasing. The right side is heading to the positive infinity. The left side is also heading to the positive infinity. So by just looking at this graph, you can say this part is increasing, this part is decreasing. So increasing intervals from negative infinity till 0, decreasing 0 to positive infinity. And for the local extrema, even though it's increasing at first and decreasing, there's no maximum here. See, that's very clear on the graph that there is no maximum point, no minimum point. Okay. Another rational function. Okay, let's find critical values first by finding the derivative. F prime of x equals derivative of top 2x times bottom x squared minus 9 minus top x squared times derivative of bottom 2x over square of the bottom x squared minus 9 squared. Let's simplify this a bit. You distribute, subtract and stuff. You can do the calculations. At the end, we will have negative 18x at the top, x squared minus 9 squared at the bottom. Okay, this is the derivative. So remember, we have two conditions. Since it's rational, we have to check both. First condition, derivative being equal to 0. Second condition, derivative being undefined. If derivative is 0, you equalize top to 0, negative 18x to 0, then x is 0. Is this critical value? When I put this back, does it make the function defined? Let's put 0 back. 0 over 0 minus 9, 0 minus 9, 0 over minus 9, 0. So it is defined. Since it is defined, we can say x equals 0 is critical value. Alright, I got one critical value. What about the bottom? What makes denominator 0 makes the derivative undefined, so just equalize denominators to 0. X squared minus 9 squared to 0. Then x squared minus 9 is 0, x squared is 9, then x is plus and minus 3. Are they our critical values? We need to check. Is f of 3 defined? Is f of negative 3 defined? When you put 3 back, it makes denominator 0, so undefined. Put negative 3 back in the original function, it also makes denominator 0, so they are both undefined. So x equals plus minus 3 are not critical value. So we have only one critical value. So remember from the previous question, whether we have critical value or not, whether the values that we found are critical value or not, we have to use all of the numbers on the table of variations to determine the sign of each region. Okay, using 0 only is not enough. We have to use all of them to make a table. So let's make a table. From negative infinity to negative 3, and in between we have 0, and we have 3, and positive infinity. We are done. F prime, F. Alright, let's check the sign of each region. Let's pick a number more than 3. No matter what number you use for x here in the denominator, it's going to be positive because you're squaring it. Number bigger than 3 makes the top negative, so the right side is negative. Pick a number between 0 and 3, like 2, it's also negative. See, without using a number from each region, if I directly start with negative and change the sign to positive, negative, positive, I would make a huge mistake. I have to be careful because there's a double root at 3. I cannot change the sign on each side of 3. So it's better, safest to pick a number from each region. So let's pick a number less than 0, between negative 3 and 0. Like negative 1, negative negative makes positive. Pick another number less than negative 3, negative negative makes positive. Positive means function is increasing, negative means decreasing. So see, those two numbers are not critical, so they don't yield local extrema. Only 0 is critical value. It has a local maximum, right? Increasing at first and then decreasing. So maximum at 0. For the others, we don't have an extrema. And about the increasing and decreasing intervals, from negative infinity till negative 3, union negative 3 to 0. A question may come into your minds. Since we have two increasing regions, can't we combine them and say it's from negative infinity to 0 instead of using a union? Can we do that? What do you think? We cannot use that. We have to use union because at negative 3 function is not increasing. At negative 3, function is not increasing, so we cannot say from negative infinity to 0. We have to use union. Decreasing interval, similarly, we cannot say 0 to infinity. We have to say 0 to 3 union, 3 to infinity. All right. 0 to 3 union, 3 to infinity. All right. Okay, these are the increasing, decreasing intervals. We already found critical value, no local maximum or no local minimum. There is just maximum. These are the things we are supposed to find for that question. All right. Okay, we are done with rational functions too. Now, let's continue with absolute value functions. So for absolute value functions, we can answer the question for two different ways. One of which is if your function is written in this way, positive in front of the absolute value and your critical value, let's say b. You know what critical value for absolute value is? It is the number that makes inside absolute value 0. When you equalize inside absolute value to 0, b is the critical value. So when you make a table of variations, you put b, and on the right start with positive because the sign of the absolute value is positive, and the other part of the other side will be negative. Negative means decreasing, positive means increasing. So this is how you can identify increasing and decreasing intervals and local maximum or minimum. Here, if you have negative in front of the absolute value, this time you have to start with negative on the right and the other side will be positive, so you'll have a local maximum. So this is a way of answering the question. Another way is using a graph, of course. Since absolute values are the parent functions, you know how to transform them and how to sketch their graph. You can simply sketch their graph and identify increasing, decreasing intervals and local extrema too. So let's take a look at the first question and answer the question by using both of the ways. Exercise 19 and a ministry question. So in this question, we have 5 minus absolute value x minus 5. What is the critical value? What makes inside absolute value equal to 0, which is 5. So 5 is the critical value. So you make a table, put 5. So let's check the sign in front of the absolute value, which is positive and negative. Start with negative on the left. So the right side will on the right, left side will be positive. This is your f prime. So the f will be then increasing in here, decreasing here. So we can say the function is increasing from negative infinity to 5 and decreasing from 5 to infinity. Right, this is pretty simple. If you know the idea of this, idea of making the table by using the sign and stuff. The second way is using the graph. You know how to graph. It's an absolute value function, V-shaped function. There's minus in front. Your graph is upside down. You have to move your graph. Since there's minus 5, 5 units to the right, and plus 5 is outside, 5 units up. 5 units right, 5 units up, and graph is upside down. This is your function. So in this function, this region is increasing, this region is decreasing, this one is local maximum. So this is the way. This is another way of finding intervals and local extrema. So on this table also, I forgot, this is local maximum because it's increasing at first and decreasing. All right. Absolute value functions are easy. Okay, let's take a look at another type of question. We have a test question here. It's in the test prep part and it's a ministry question. Which function has exactly two local extrema? So in order for us to have two local extrema, we should have two critical values, right? So let's find critical values of each option. Option A. Find derivative. F prime of x equals derivative of x is 1, derivative of ln x is 1 over x. Let's equalize derivative to 0. So 1 is minus 1 over x, then x is minus 1. Is f of minus 1 defined? Yes, defined. So this is your critical value then. So do you have any critical value from the undefined condition? If f prime is undefined, then denominator is 0. If denominator is 0, is function defined at 0? No. ln 0 is undefined, so there is no critical value from this case. So there is only one critical value. Since there is one critical value, one local extrema. So the first option is false. Only one local extrema. Option B. So this is an absolute value function, x minus 2, absolute value, 2 units to the right. We have just one local extrema. Just one. Without solving the question, you can just answer it by eyes. So B is also false. Option C. Option C, it's polynomial. C and D are both polynomial, so there is no number that makes the derivative undefined. So we just check derivative being 0. F prime of x equals, derivative here is 3x squared plus 6, equalize it to 0. X squared will be negative 2, right? Is it possible? X squared being negative? No, it's impossible. There's no critical value, no extrema then. C is also false. So the answer should be D then. Why? Let's see. What is derivative in D? 3x squared minus 6 equals 0. So in exam, I don't have to solve B, of course, because I already eliminated 3 options. Now I just want to show you how it has two extrema. 6 to the other side, x squared is 2, so x is plus and minus square root of 2. Since I have two different values, I will probably have two different local extrema. So this is the answer. Alright. Another type of question, an exercise question and a ministry question. This is pretty common function in the recent years. I see a cusp here, x to the power of 2 over 3 minus 4. In order to find the find these stuff, increasing, decreasing intervals, extrema, critical values and stuff, we don't have to do the steps actually. We can immediately graph the function since we know it's a cusp. You know how cusp functions look like? It's like that, right? Since there's translation 4 units down, so our function will look like this. If when you know the shape of the graph, you will save a lot of time. So when you know the shape of the graph is like that, you can immediately tell critical value. So what is the critical value? It's x equals 0. And what is the increasing intervals? It is from 0 to infinity. What is the decreasing interval? It is from negative infinity to 0. What about local extrema? Since this is the minimum point, we have local minimum at x equals 0, y equals negative 4. local minimum at 0, -4. If the question is asking about minimum local extrema points, we have to find y. If it asks about only x value, we just look at the x. Okay, if you want to solve it in a long way, of course you can solve it just by find the derivative. F prime of x equals, derivative of this one is 2 over 3 in front, x to the power of 2 over 3 minus 1, -1 over 3. And yeah, let's simplify this. Bring x down to get rid of this negative exponent. 2 over 3x to the 1/3. So this is the derivative. So we have two cases. First case, derivative being equal to 0, then top is equal to 0, which is impossible. So there is no critical value from this condition. Second condition, function, the derivative being undefined, which means the denominator is being equal to 0. In this case, x is equal to 0. So is this number our critical value? We have to check. See if it makes the original function defined. When you put this back, 0 minus 4. Minus 4, yes, it is defined, no problem. Since the function is defined at x equals 0, then x equals 0 is critical value. So we got our critical value. Then we can make table of variations. 0, which is our critical value, from -infinity to +infinity, f prime f. So let's pick a number more than 0, like 1, put it back. It's gonna make the derivative positive. Pick a number less than 0, like -1, it's gonna make the derivative negative. Negative means decreasing, positive means increasing. So here we see the decreasing interval, here increasing interval. So at that value we have local minimum. So everything is clear on this table. If you wanna follow the steps, take derivative and do the steps. Right, so you generally have two different ways for the functions that we are familiar with the graph. All right. Okay, another question, a test prep question and a ministry exam question. So a similar question came one more time. This is not the only ministry question about this type. It's asking about the decreasing interval only. The other ministry question, the same function, it was asking about increasing interval. So let's see what happens. Derivative of function is, derivative of exponentials is derivative of the exponent, which is 3x squared minus 12x times the original function. So it is impossible for this function to be undefined, so we are going to equalize it to 0. And it's also impossible for exponential function to be 0. It is never 0, remember, no matter what x value you put here, since the base is e, it's never gonna be 0. So you just equalize this factor to 0 then. If 3x squared minus 12x is 0, then take 3x out as a common factor. Then your x is 0 and 4. Are they our critical values? When you try this in the original function, yes, they will be. F of 0 and f of 4 will be defined. So they are our critical values. Let's make a table of variations by using those two numbers, 0 and 4, of course, from -infinity to +infinity. F prime f. Okay, now pick a number more than 4, like 5. When you put 5 back, it's gonna make it positive. Pick a number between 0 and 4, like 1. It's It's gonna make it negative. Pick a number less than 0, like -1. Negative, negative makes positive. So these two are increasing intervals. This is decreasing interval. So we have only one decreasing interval, which is from 0 to 4. Option D. All right. So actually there are two ministry questions by the same idea.